y'all doing today? Good. Did your first period teacher talk to you about the crazy week? All right. For the benefit of those that said no. Tuesday, Wednesday is math testing, so it's long periods. On Tuesday, you meet 1, 2, 3, and on Wednesday, you meet 4, 5, 6. Kind of double period thing. Lunch, I'm not sure how lunch goes. Lunch is based on the floor of the third class of the day. So I guess that would be third period on the first day and sixth period on the second day. So, as far as my class goes, we will meet tomorrow but not Wednesday. Also, according to schedule, you have a test on Friday. All righty then. We'll talk more about that later. It'll be through last week's material, and you'll be great. The papers, gosh, you might have been shocked by a little paper back there. 3 sets of paper. I'm going to do a double lesson. Are you ready? Let's move. Monday morning double lesson. Calculus? Yeah. It's the perfect storm. Here we go. The first part is the yellow sheet. It's pre-calculus material. Green sheet, excuse me. Green sheet. It's green. Did I do it right? Is green the green stuff? Yes. Okay. The first idea, set 22, it's a bit of a mixture of 2 pre-calc ideas, trig and conic sections. I am going to boil this down. I'm not going to do a full rehash of all the pre-calc stuff you should and must know. Yes? Yes. Only the stuff that's most applicable for mine and the calculus part of this. Okay, then. Here we go. First, I expect you to be able to work with trig, either graphs or equations, where there is an argument or a stretch, like sine of 2 theta or cosine of 3 theta. All right? First, let's review how that affects the period. I think we covered on Friday how if you multiply x by a factor, it causes a horizontal stretch or squish. Yes? All right. Now, that would then affect the graph, if you're looking graphically, or how many solutions you can get if you're solving an equation. First, though, let's talk period. Anytime you find the period of a sinusoid or a cosine curve, or for that matter, secant or cosecant, the period is always the normal period, 2 pi, divided by the coefficient, whatever is in the problem n, all right? Tangent's normal period is pi, negative pi over 2 to pi over 2, for example. Same with cotangent, and so that period would be pi affected by the coefficient. So if you find the period by taking 2 pi and dividing by the coefficient, this first problem would have a period of 2 pi over the coefficient 5. The period would be 2 pi over 5. In this case, the second case, the period would be 2 pi divided by 3 halves, which is 2 pi times 2 thirds, or 4 pi over 3. The wave would have a wavelength of 4 pi over 3. Really? Really? Okay. Tangent of 3x. The normal period is pi for tangent, so in this case, the wave would have a period of pi over 3. And that would actually mean the middle curve would be negative pi over 6 to pi over 6. Instead of negative pi over 2 to pi over 2 divided by 3, and it's negative pi over 6 to pi over 6. All right, now these guys are kind of funky for students, but they're important in terms of using this in real-life modeling. If you go on to be a mathematician or an applied mathematician or an operations research guy, all those careers we can do with math. But first, let's go here. What's the period? 2 thirds, okay? Now, students tend to get cooped out a little when you see a pi in the argument, but that's actually real life used all the time. It's what takes a period that has pi's in it and takes out the pi. You know, if I say how long is a year, you don't say it's 365 pi days. It's just 365. You don't have that pi in there. And so by virtue of putting a pi in the period, it knocks out the pi, and you get a plain old number, right? Now that's very common, and you'll see that frequently. So what's the last period then? 4, yeah. Okay. So if I were doing a sinusoid, doesn't a positive sine curve look like this? And if the period is 4, what's a half period? 2, and a quarter period? 1. And you could just use a nice 1 scale for that one. Let's talk graphics, shall we? I'm a little picky about this. I used to just deal with it and let you mangle them, but I had too many times where I was pulling up my hair while I was grading, looking at your work, or looking at previous students' work, and I don't have hair to lose, so I need to make sure that you do this well, so it makes me more sane. This is my method for graphing a sinusoid. Now, if this is a little new to you, that's okay, because Saxon book, I feel, does a really poor job of explaining graphing a sinusoid. So this is what I would like to see. Say you're graphing that our cosine curve down there. You see that? All right. So the first thing I would expect is that you know the vertical component to this. When you add something outside the function, what does that do to the graph? Shifts it up. So whereas cosine is normally centered at 0, now it's going to be centered around 3. Okay. Now, if you want to dot that in to mark your center line, you can. You don't have to. Okay. You don't want to get the graph too busy. What does the 4 do? If you multiply the function by a factor, that causes a stretch. Vertical or horizontal stretch? Vertical. Instead of being an amplitude of 1, going up from the center line up 1, now you're going to go up, center line up 4, and down 4. Amplitude is 4, go up 4, down 4 from the center line. So we're going to have a max of 7. The wave will not go above that. And a min of 3 minus 4, or negative 1. I know my graph will be in there. How? Okay. Now the horizontal component. What's the period? We just did this part. 2 pi divided by the coefficient 2 makes the period pi, yes? Now, in terms of the shape, let's do a rough draft here. The shape of positive cosine, the parent graph of positive cosine looks like that. I require, in terms of especially for calculus, all the maximums, minimums, and the inflection points, which is where the graph changes from concave up to concave down. In other words, these quarter wave points, all those must be shown accurately, every one. Okay? So in order to show those accurately, you first take a wave, half the wave, quarter the wave. Every quarter wave will be pi over 4. Yes? I want to be able to locate that accurately. But before we go a graph, let's talk the last component. This is shifted right pi over 6. Now in terms of locating points then, my starting point is pi over 6, yeah? Okay. But then I'm going to shift that pi over 4. Now this then goes to choosing a good scale. To me, this is the most important part. Choose an X scale that will allow you to find the shift and every quarter wave. To do that, then, you want the greatest common factor between a quarter wave, and the shift. You want the greatest common factor between pi over 4 and pi over 6. I know it's been a while since you did greatest common factor, but you want a thing that goes into both. Okay? So what's a denomination that would go into both? 12, pi over 12. You're going to choose a scale of pi over 12. Now, in terms of my preference, I don't want you to show a million different parameters. Mark it once, and that's it. All right? I don't need every mark shown. It gets too busy. Now we're ready to go here. This point that did start at 0 is going to be shifted right pi over 6. Where will it be then? In terms of pi over 12, that would be 2 pi over 12. Do I put that at the max, the center, or the mid? Cosine wave starts at the max. And so you should start your wave right there at pi over 6. Now, once you get good at this, you'll find that after that, with the scale, home free. Every quarter wave is pi over 4. How many boxes is that? 3. Okay. So from that point, you're just going to count boxes and put a dot. 1, 2, 3, center line. In another 3 boxes, where will it be? At the minimum. In another 3 boxes, where will it be? Center line. Furthermore, we can go backwards. Going backwards from that first point, 1, 2, 3, center line, min or max? Center line. 1, 2, 3, center line, min or max? Min. 1, 2, 3, center line, min or max? Center line, 1, 2, 3, max. That is accurate at every critical point for calculus purposes. Okay? Now, choosing the scale is the hardest part. Once that horizontal scale is chosen, it's just 1, 2, 3, point 1, 2, 3, point 1, 2, 3, point, or whatever, however many boxes it might be. Okay, I think there's 2 on tonight's homework for you to practice. Next idea, conic sections. Conic sections. These are important for, gosh, in real life they happen quite a bit. The conic sections, if you recall, are circles, which obviously those happen all the time in life. Parabolas, those model projectile movement, useful in real life. Ellipse, that models planetary motion and particle motion at the atomic level. Hyperbola is this, it's kind of hard to get hyperbola. But I was reading a book this summer, and GPS, the whole idea of GPS is based on hyperbolas. It's really cool. We'll have to go over that sometime. But all these come from the rather crazy abstract notion of taking cones and slicing them some ways, which who cares? But that abstract idea has real life applications, as often happens. You start with this thing that, I don't know how I'd use this, and it actually can be used, so it turns out. Now, I'm going to go through this at kind of a different angle here. First, let's talk about what clean ones might look like, just to remind you. What's the graph of this first one? Circle, center at the origin with the radius of 2. What's the next one? Okay, the minus is the star. That shows. This subtraction indicates this is hyperbola. Does it open sideways or vertically? Sideways, okay? It looks like this. All right, the next one. Now that's been tweaked a little. You might actually prefer to divide 36 over. What's that? Kind of like a circle. It's x squared plus y squared, but what does multiplying do to a graph? Stretches it, stretches x, so it's going to take a circle and stretch x, making it an ellipse, okay? So, with that in mind, this would actually have a horizontal stretch of 2 and a vertical stretch of, it's actually 6, it's more stretched vertically. I'm not sure how that works, but I'll leave it at that. All right, you follow? X equals y squared. Don't do a lot of that in our book, but that is a parabola opening sideways. If you see only one square, it's a parabola. If the x is squared, it's a normal parabola. If the y is squared, it's a sideways opening parabola. X squared plus 4x, what is that? It's a y equals x squared parabola. Tell me, what's the quickest way to get a good graph of that? factor it. The roots are 0 and -4. And what does that tell me about the graph? The y-intercepts, yes. Good job. The y-intercepts, you bet. All right, last one. What is it? Square minus square. Hyperbola opening sideways or vertically? Vertically. Like this. Okay. Now, in terms of graph, then, and in calculus, you'll be dealing with a little different forms of these. Mostly these are non-functions. Do you agree that they fail the vertical line test? If you put in 1x, you actually get out 2y's in most of those cases, with the only exception being this one. However, you often want them to be functions, either so you can do calculus on them, or you can put them into your calculator better. So what I'm showing you here is actually conic sections that look slightly different. I want you to tell me what these might look like. Now, it might help to square and move variables to one side, constants to the other, to make your decision. Let me show you what I mean. First of all, let me pretend this is a y for right now, okay? I don't look at that. It's tempting, first of all, don't fall into the ridiculously silly trap of saying, oh, that's a square root function if it's like this. It does not. Square both sides. Y squared. If I see a root and an x squared, I think conic, first of all. All right, so y squared equals 36 minus x squared. Wait. If I get the x squared over, I get x squared plus y squared equals 36. So what is the graph? Circle, but how about the function part of this? It's just half, okay? If you went backwards, when you square rooted, wouldn't y be plus or minus that square root? But they're only giving you the plus side, so only positive y's here. Only positive y's. It's a circle, like you said, but only positive y's, so it's just the top half. All right. Try the second one on your own. See what you think that graph would be. Square both sides, play with it a little. Decide top half, bottom half. Okay. First of all, which conic? Hyperbola. Is it top half, or is it opening sideways or vertically? Vertically, and so top half or bottom half? Top half. It would look like that. Always take care to remember hyperbolas are quasi-linear. They are not parabola shapes. I know it feels like the parabolas in here because they're bending, but that's just at the middle. As x gets infinitely large, it starts to approach a line. Think calculus, my friends. As x gets infinitely large, does 36 change 10 very much? Well, yeah, it has a pretty good effect. But if you add 36 to a trillion, is that doing anything? Okay, well, let me tell you what I mean then. Think about this as x gets large. This gets infinitely large. This starts to mean nothing. And so y starts to approach just the square root of x squared, or x, a line. Okay, that's what our hyperbola is coming from, is the limit as x goes to infinity starts to approach this linear behavior. So that's what follows those asymptotes, all right? Try the next one. What kind of conic? ellipse, normally the x change would be 2 to the left, 2 to the right. Y change is 6 up, 6 down. Whole conic or just a part? Just a part. If y is negative, I only want the bottom half. So it's actually, if you were to graph that in your calculator, you'd see a lower half of an ellipse. Not a problem. This one hopefully is pretty easy. What does that graph look like? Those two graphs. Square root looks, you should know what a square root graph looks like. It looks like that. What does negative square root graph look like? Left side or below? Below. Y negative would be down here. And so that is nothing but y squared equals x. It's a parabola opening sideways. Okay, do the last two, then we'll move along. There are some various homeworks coming your way. Y'all put grades in after school today? If you didn't turn any of those in, you can turn them in today for half credit. After today, there will be no credit. How'd you do on G? Did you get top half of a sideways opening hyperbola? Is this going well, or is this going badly? Okay, I'll take that. Thank you for giving me some neck action, if not words. All right, try the last one. Let's get some people participating here. Let's see, Luke Shaw, where are you at? You're Luke?
No.
Hi, Luke. Did you get to the last one yet? Oh, okay. Oh, good point. Sorry about that. Let's see. How about Charity? Where you at? Hi, how are you, Charity? You already participated in my mind. Thanks for that. Participating. Kenny, where you at? Hi, Kenny. The last one. What did you say, Laconic? Are you at there yet? Not there yet? What? Hyperbola. Everybody else agree, disagree? I haven't done it yet. Anybody else? Shout out any other answers if you disagree. Circle. Okay. Any others? Okay. So to decide, I don't look at this form and know. So I square both sides. Call it y squared equals 9 minus x squared. That feels like hyperbola because it's got a negative, so on that surface it seems right. But when I move x squared over, remember the idea is to get the x's and y's together. At that point it starts to feel like circle. Top half, bottom half. Well, if y is negative, it's bottom half. You follow? Okay. Great job. Would you get out your calculator, please? Would you get out your calculator, please? Do you remember how to put a conic that's ugly into your calculator? Okay, a little yes, a little no, I hear. So, first of all, if you have an updated Inspire, like mine is, in the graphing menu, you can actually go to Menu, and in the graph type, you can take an equation, and it gives you lines, parabolas, circles, ellipses, hyperbolas, or general form conics. Now, you don't actually have to be able to, you don't actually have to be able to look at this and tell which conic it is, although I would like that you can tell me it is a dot, 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 hyperbola. Why do you know, how do you know it's a hyperbola? Yeah, the squares are different signs. If it's squares are different signs, it's hyperbola. Now, this is not Pretty Princess set up standard form hyperbola. This is what's called general form. So when you go to put this in your calculator, if you have an updated Inspire and you have that equation button, you would go to conic and choose the general form and plug that in. If you plug in x squared minus y squared plus 2xy, I'm going to write this over here so I have it to look at. X squared minus y squared plus 2x minus 4y plus 9. Does that say plus? Minus 9, thank you. Minus 9 equals 0. Then you're going to go something like x squared. That xy term, if you go on to analytic geometry, that's the worst. It causes rotation of axes. It's a huge mess. The calculator, thankfully, does it very nicely. But it would cause an ellipse to be at a diagonal in 2 space. And 3 space is even worse. But at any rate, we don't have an xy term, so call it 0. What's this guy? -1. How many x's? 2 minus 4 minus 4. All right, now it might be the case that you don't have that menu or you have a TI-84. If you graph that, it should look like that. So far, so good. Some of you. Raise your hand, please, if you have that function in your calculator. Okay, now mine was not updated, so I didn't have, my handheld didn't have that function, so that stinks. For those who do have it, please continue on and put in y equals x plus 3, and then find the intersection points, which is what you are doing when you solve a system. Now, going back to those of you who are more, in my sense, I think of this as ghetto calculators, which I like to use, ghetto calculators. Other calculators, they only deal with functions. If that's the case, you must complete the square on y. Please write this down so you have it as a reference. If I complete the square on y, I would move all y's to one side, preferably so that they're positive. So I would have something like y squared plus 4y on the right side, and x squared plus 2x minus 9 on the left. Do you see what I did there? Yes? Okay. Now here's the deal. Students want to divide out a y. Your goal is to solve for y. Students want to divide out a y, and I understand on one level, but doesn't that mean then that over here you're going to have x's and y's if you solve for that? So that doesn't actually work in terms of dealing with the square. That's a no. You don't do that. Instead, to deal with the different power problems, that's actually why completing the square was invented, is to deal with the I have 2 different powers of y problem. If you complete the square, what shall you put here? 4. In order to balance, you'll put a 4. Now then, complete the square. Complete the square. Okay, so at that point, the left becomes y plus 2 squared, and the right x squared plus 2x minus 5. Now you're going to square root, call it plus or minus. Y plus 2 is plus or minus square root of x squared plus 2x minus 5. You're almost done. Solve for y, or isolate y. Y is -2 plus or minus x squared plus 2x minus 5. Now you can graph this in your calculator in two functions. Remember, the hyperbola is not one function. If you make it a function, it's got to be two pieces, the top and the bottom. So you're going to say y1 is negative 2 plus x squared plus 2x minus 5. And y2 is negative 2 minus x squared plus 2x plus 5. So doing that, that would allow you to put it into the 84. So G, delete. Oh, shoot, delete. Hang on just a second, sorry. Actually, let me go. Delete. I'm just going to go a new document. How do I clear this scratch pad? Okay, sorry. So, first graph was negative 2 plus the square root of x squared. Was it plus 2x or minus 2x? Plus 2x minus 5. Hey, there's the top half. To get the bottom half, you then do the same thing, but negative 2 minus square root. After you've got the hyperbola in, would you please find the intersection points? Shoot. Actually, maybe I should just move on in the interest of time. And in fact, I'm losing it. Okay. Did you get the intersection points, or can you get the intersection points? Is it close to it? Do you remember how to get intersection points? You better. Okay, good then. All right. That then is what I expect you to be able to do from here on out. That is, should be, hopefully, review. Let's move on to calculus. Also known as the greatest single shortcut in all of mathematics, the power rule for derivatives. Yes, at the end of this, you'll have a super shortcut, but first you have to pay your dues to earn it. So, with this, consider, and by way of review for the test, consider if you wanted the derivative of f of x equals x squared. By the definition of the derivative, you can say that f prime at any x, I want the derivative at all x, is the limit as, give me the first definition of the derivative, please. H goes to 0 of, now the slope function. H. If you don't have that deeply ingrained in your brain by Friday, you're going to be in deep doo-doo. Okay? Now, for this function, I'm talking x squared. What's the binomial expansion of x plus h squared? When I do x squared, that would mean x plus h gets squared. And so I need to review that. What's the square of x plus h? X squared plus 2xh plus h squared. So when I throw in that binomial expansion, I get x squared plus 2xh plus h squared minus x squared over h. Now, each of these cases, you're going to see the same kind of thing happening. X squared subtracts away. The remaining terms all have an h, so when you divide out an h, you will have the first term has no h's when that's gone, and the rest of the terms will have an h. So that when you take the limit, the h goes away, and it just simplifies to the second term that stayed. The derivative of x squared is 2x. Using that same idea for a cube, building towards finding a pattern is the idea. If you did x cubed, then the limit as h goes to 0 of f of x plus h minus f of x over h. Every time I write that, it's getting deeply ingrained into my brain. Becomes x plus h cubed minus x cubed over h. So, the binomial expansion of x plus h cubed, do you remember it? X cubed plus 3x squared h plus 3xh squared plus h cubed. Remember that there's really three patterns involved. The x powers decrease each time. The h powers increase each time. And then the coefficients we could actually get through Pascal's triangle or combinations if we had all the time in the world, but we don't. So, the limit as h goes to 0 of x cubed plus 3x squared h plus 3xh squared plus h cubed, if I plug that in, again, that same kind of thing is happening. The first term goes away, subtracts away. Every other term has an h, so I'll be able to divide out an h. The second term, then, the h's all go away, and the second term is a non-h kind of term. The rest will still have an h or more. So that when you take the limit, at the end of the day, the only thing left standing is the second term of the expansion, and your derivative is 3x squared. You see? Okay, last real quick then. By the binomial expansion of x plus h to the fourth, it's x to the fourth plus 4x. What's the power of x next? Cubed h to the first plus 6x to the square h squared plus 4, there's symmetry, x to the h to the, ending in h to the 4. Notice that fourth power has 5 terms, the third power has 4 terms, and so on. Oh, thank you. So, I'm skipping writing the definition this time, and I'm going to go straight to, this would be x plus h to the fourth minus x to the fourth over h, yeah? The expansion gives me x to the fourth plus 4x cubed h plus 6x squared h squared plus 4x h to the third plus h to the fourth minus x to the fourth all over h. What happens to the x to the fourths? They go away, they subtract away. What happens to the h's? Well, everything with an h is reduced by 1h. So, 4x cubed plus 6x squared h plus 4x h squared plus h cubed. As the limit of h is going to 0, this starts to approach just 4x cubed. Now, looking for trends, somebody said, wait a second. X cubed is 3x squared. It looks like what happened? The exponent, when you took the derivative, the exponent comes out front, and what happens to the new exponent? Reduce the exponent by 1. Okay. Yeah, wanted you to see where it came from. Now the question is, can we prove that with the general? And the answer is no, we don't have time, so instead let's just go to the power rule. The power rule, if you take the derivative of some x to a power, it's bring the power down and reduce it by 1. It's crucial that you see this in all its forms. Obviously, when you take a derivative on x to the 7th, it's easy. The derivative is 7x to the 6th. Isn't that way better than doing the definition of the derivative? Yes, it is. But it's also important that you recognize that this is applicable to roots and fractions. For example, the square root of x is the same as x to a power. X to what power? 1/2. If you rewrite first, if you're given a root or a fraction, you rewrite it as an exponent, then the power rule can be used. What's the derivative of x to the half? 1/2 x to the negative 1/2, which as a multiple choice answer might be written as 1/2 root x. Okay? What about this? If I do a rewrite on this, what is 1/3 root of x as an x to a power? Negative 1/3. The negative is there because it's in the denominator, and the fraction is there because it's the root. So when you take the derivative, g prime would be negative 1/3 x to the negative 4/3. So I suppose if you wanted to, you don't have to, believe me, you can leave it that way, but I suppose as a multiple choice it could be written that way. Usually you just leave it as a power. That's the power rule. It's delightful. Boom. Done. All right. So we have questions on, do you still have 2021 and 21-22? Yeah. Let's get 2021 knocked out at the very least. I want that turned in today, and we'll get caught up on the long day tomorrow. Questions on 2021, please. If you have them, let me find my key if I had it. Or did it go well? I did post the key. Let me know if you have questions on 2021. Call it 20, set 20 number this, or set 21 number that. Yes? 20 number one. Okay. Any others? Feel free to add them as we go. 20 number one. Yes?
2021,
21 number 6?
16 on 20.
16 on 21? 20. I'm sorry. I didn't get it. 16 on 20. So I don't waste my time. Do I have that correct?
Yeah.
I do. I really am that type of. All right. So, set 20, number 1. Okay. Let's see how this goes. Ooh. By the way, I remind you, this was kind of a harsh wake-up call for the EC students. When you when you receive help, whether from your dad or your brother, your buddy in class, or me, you should be doing this in ink on the homework. Okay, that's crucial for me as your teacher, so I know, hey, they're having trouble with this, hey, they're having trouble with that. It's also crucial for you because if I give you a homework quiz, if it's in ink, you'll be able to use that homework. If it's in pencil, well, I assumed you knew how to do that the first time. You did it in pencil, you must have done it right the first time, you cannot use it. Okay? So, basically then, just like my syllabus says, when you're making corrections, when you're doing a problem you had trouble with, it should be in some color, not pencil. Okay? So, you should, if you're asking these questions or going over corrections, you should be working pencil. Or, sorry, ink. 20 number 1. Yeah, this was kooky. These kicked my butt when I was first doing them in your shoes. Didn't quite get the idea. They're really prepping you for a calculus idea coming later called optimization. So you're trying to express the distance from 2, 3 to any point x, y on this here graph, y equal to x plus 1. That's the first part. In terms of x is the second part. Now, a graph's not necessary once you get good at these, but it helps me explain. So I know what point 2, 3 is, obviously. It looks like this. And y equals 2x plus 1 would look like this. All right? Now they want you to express the distance from 2, 3 to xy. Well, 2, 3 to xy, you're talking any point on the line. Now that distance could look like this, or 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 like this. It depends on the point they choose. So I'm not going to get a number here. I'm going to get a function kind of depending on what point I choose. Well, let's start with the distance formula. Remember how to find distance between 2 points? The form of the Pythagorean theorem? Yeah, sounds like it. It's like this. Okay, that's like one part of the triangle, of the right triangle. And then this is like the other part of the right triangle. Square to get the Pythagorean theorem and square root it to get the distance rather than the distance squared, all right? So distance formula is just the form of the Pythagorean theorem. There's a lot more complications. So if I plug in the things, it doesn't matter what order, but x minus x. 2 minus x or x minus 2 squared. There's the x's. And the difference in the y is squared. Y minus 3 squared. Okay. Now we just did the first part of the problem. There's the distance from 2, 3 to xy. Boom. Now we haven't finished though, because it says in terms of x only. Why would they care? Why? Why do they want that? If I said to graph this, could you graph it in your calculator? No, it's got 3 variables, okay? In order to get this in your calculator, you need to get it down to 2 variables. And also to do calculus on this, you want to get to 2 variables. That's why the second part is there. It's not to make your life hard. They're prepping you for a calculus idea. To get this down to 2 variables, they want it in terms of x only. So what could I put in y's place? Well, what is y equal to? Yeah, y is 2x plus 1. So in place of y, I could put 2x plus 1. Oops, the minus 3 is still there. And then I've answered the question. There's the distance expressed with only x, not y. Does that make sense? Okay. In calculus, then you could optimize that. You'd take the derivative on that. You'd have to use the chain rule and lots of great stuff. And the pre-algebra or the pre-calc stuff of solving it would be hairy, but we'll get there. 2016. Is that still a question? I assume you didn't have an epiphany or anything? Okay. The interval notation is, sometimes I change these. I didn't change that. No, I didn't. Okay. Interval notation to describe the intervals for which f lies above the x-axis. Glad you asked. X minus 2. You really need to be proficient in graphing factored form. Factored form gives you, this is factored form, which makes it easier to find x-intercepts. And this is a cube. And so it looks like one of those two shapes, positive x cubed, following those x-intercepts. So that's, I did a 3-dimensional graph, or a 2-dimensional graph. You could have done a sign chart, but I know the zeros, or what are the zeros? Excuse me. You tell me, what are the zeros? 2, -4, and 0. Now, attaching the appropriate shape to those zeros, the graph would look something like that. With that, I'm home free. Where does the f lie above the x-axis, or where does the graph lie above the x-axis? So it's surely above the x-axis in this interval of x. Now, interval notation, remember, is lower to higher. The lower bound of that is -4, and the higher bound is 0. You indicate whether to include the endpoints or not with parentheses or brackets. Now, it's not actually above the x-axis at that point, so I don't want to include that point. I'm going to use a parenthesis. Now, if there's another set, you typically write union for, hey, there's another part to the solution. I would never count off if you didn't write that, but that's the right way to do this. The next interval is lower to higher. What's the lower to higher of that region? 2 is the lower. The higher, it's unbounded, so it goes to infinity. And again, Hey, the 7th hour is free today, so you finally get a 7th hour. If you have more questions, come in. This one is due, the other one's not. I believe 2021 is due today. Understood? Okay. Have a great day. Okay. Thank you, operator.